Good morning. My name is Colin Gedge, and we're going to start right up. I see that most of you people are in your seats. If somebody could just send me a quick message saying sound's still coming in loud and clear, that would be great. I think that, let's see, I think I need to press a show my screen button here. There we go. I'm showing the wrong screen, unfortunately. Let me just figure out how to do that. It's a little bit early in the morning for me here on the West Coast, having just gotten up at around 5 o'clock. I think we're showing the right screen now, so everyone says that I'm coming in loud and clear. We will be making a copy of this webinar and putting it on our website. It's also on our YouTube channel. You can just look under Retrotec webinars, and you can probably see most of our webinars on there, so there will be a copy of it there. This is the third or fourth time I've done this webinar, and it keeps getting longer and more complicated, so it's quite likely that we'll run over, particularly if we've got a lot of questions, which of course I welcome, but it's quite likely it will run over. It's not really meant to be a training course per se, although a lot of the information is very, very useful. We do have an online training course, 3 different levels that covers all of this material. I'm not going to focus on these as much as I've done in the past, but suffice it to say that the Door Fan test has replaced the discharge test, which discharge test was costly, disruptive, but its main negative feature was its environmental impact, which deep sixed it. So it's seldom used anymore except in CO2 installations. So we have a couple of quotes here from section 5.6. I think this is in ISO, this one's in NFPA, and they both say it should be inspected every 12 months, and in many countries it's required that the enclosure be reevaluated every 12 months, and if there's still doubt exists, to check it again with the door fan, which is what this instrument looks like over here. It fits into a door, hence door, and there's a fan in there, a calibrated fan that measures the leakage. There are 2 reasons to be using it now. There used to be only one. And the second reason is to measure the pressure relief venting, which is a requirement of NFPA. And so far in the U.S., we've got roughly about half of the installers in the U.S. using the new software and doing peak pressure evaluations. This is the actual section in NFPA that talks about the requirement. Just a quick note on the NFPA, I didn't include this in my introduction, but back in 1984, I was the one who discovered that door fans could be used to determine whether or not a discharge test would be successful, and 3 years later managed to write a standard for NFPA that showed people how to use a door fan instead of doing a discharge test. And as most of you now know, now it's being performed in about 60 countries. ISO's adopted it, the European norm has adopted it, and so on. So it's become pretty popular. I spent the last 5 or 6 years or so rewriting most of the NFPA standard in order to make enclosures pass more easily when they should pass, and at the same time to allow them to pass the peak pressure requirements or to measure the effectiveness of vents. And you can see here with the old NFPA, we've got an FM200. One with the old NFPA would give it 9.3 minute and fail. The new one would give 10.4. Not a lot, but around about 12% improvement there. And then on the peak pressure side, if the peak pressure requirement was 250, the new NFPA would pass, the old NFPA would not pass. What's important here is to determine whether or not a room should legitimately pass or not, and that's what the new standard does. I've also worked on the ISO standard and revised all of their equations, and I'm intimately familiar with pretty much every word in the enclosure integrity part. So we support roughly about 3,000 people worldwide that do enclosure integrity tests. So there's not too much that we don't know about it. Most of the manufacturers of equipment and agents rely on us for peak pressure and enclosure integrity, meaning hold time issues. The ISO 14520 2006 edition also requires a door fan test. The calculations are different. It uses what's called a wide interface, which decreases hold time by 25%. The new proposals that we have accepted by the ISO committee remove some of that conservatism, and in some cases it's extremely conservative. The NFPA is optimistic in some cases, but the truth actually sits somewhere between the two, and we're in the process of resolving that. One of the issues with the ISO standard is that in one of the sections it requires protection to 90% of enclosure height. Many countries have written that out of their standard, that they don't require that. It forces the enclosure to be exceptionally tight, I think unnecessarily tight, and forces the use of PRVs in every installation, which can be a good thing, I guess, but it does provide an element of risk in that the enclosures are so tight that if the system discharged and the vents didn't work, the room has danger of being damaged, and in some cases it's quite likely. So the first thing we're going to talk about is peak pressure. In the sequence of events, an agent is discharged, and unfortunately in these cases a little bit too much pressure was created. If an agent is discharged into the enclosure, and in the case of an inert, for example, which most of you would be most familiar with, certainly from a peak pressure standpoint, we get a very short-term, short-duration pressure spike, or it spikes up where the valve opens wide open and goes up to its maximum point in 2 or 3 seconds and then drops off exponentially. What wasn't known until we did our research study was that the halocarbons can produce just as much peak pressure. If we were to discharge this into the same enclosure, a halocarbon and an inert, the inert would produce much more pressure. However, because the halocarbons are much heavier, they must be much, much tighter, so therefore they get more pressure. So in the real world, they often produce roughly about the same amount of pressure, but it depends. One of the things we discovered in our research is that when a halocarbon is released, there's a very, very rapid drop in temperature, which produces a negative pressure spike. This curve over here is an inert, and you can see that there's a much more gradual cooling. We're only cooling, what is this, about 10 degrees F or 13 degrees F, which is, what's that, 7 degrees C. The cooling with the both halocarbons that we have here, 227 and Novec, much, much more of a negative pressure creation. But the important part is the time at which it takes. Here, this cooling of the room happens in 4 or 5 seconds, and that's what produces a negative pressure spike that looks something like this. So this one looks like a characteristic curve of Novec, has a very high heat content. So this is zero pressure. Upon discharge, the pressure drops. As the agent, excuse me, after most of the agent is in the enclosure, there is a period where the nitrogen in the tank is blowing down, and there's not much more agent coming into the room. The agent flashing from a liquid to a gas is what causes a cooling, just like if you put alcohol on your hand and it evaporates, you get cooling. The positive pressure spike is a result of increased mass coming into the room, no more cooling going on, as you saw in the previous graph, and a bit of a positive pressure spike. This negative pressure spike is determined by the relative humidity. If the relative humidity is very low, this pressure spike is very large. If the relative humidity is very high, this negative pressure spike can disappear altogether. And the way I like to explain that is if we try to get a liquid to evaporate in 100% relative humidity, it doesn't evaporate very fast, so therefore there's not much cooling. So along with everything else, when we're dealing with the halocarbon, we have to know the range of humidities that we're expecting in that enclosure to determine the range of peak pressures that we might experience. Okay. So again, here's another halocarbon, in this case HFC 125. You notice they all have the negative spike followed by the positive spike. And incidentally, while the presentation goes on, if you have any questions, you can type them into your question window and they'll pop up. And if it's relevant, we'll answer them during the presentation. If not, we'll try and answer them later. If you don't get them answered, by all means, send me an email. Colin, C-O-L-I-N, at retrotec.com. So this negative spike that we have here is dependent upon what we call the leak to volume ratio. So if we have two enclosures, one's twice as large, and if the second one has twice the leakage of the first, they will have pretty much exactly the same peak pressure. So here we see as the enclosure gets tighter, the peak pressures become greater, and all it does is just kind of magnify the size of that curve. And if the leak to volume ratio is sufficiently small, then we may often have to install a PRV to control it. This is kind of a crazy graph that shows you humidity correction. The red line is the humidity correction required for halocarbon on the negative direction. So you can see we have some kind of an inverse relationship. As the humidity rises, the factor that we factor the peak pressure up drops. So there's some important design features that must be considered for peak pressure. First thing is we have to know the enclosure strength. We need to determine the range of leak to volume ratios and have to estimate the peak pressure based on the agent type, the type of valve, discharge rate, and the leak to volume ratio. And then that would go into the sizing of the vents. And NFPA requires, the working plans require an estimate of the maximum peak pressure, and a specified pressure limit has to be included. The one below here is, I think, Annex D1. Oh, I'm sorry, this is NFPA. And the enclosure, of course, must be capable of withstanding that pressure. So there's various bits and pieces spread throughout the standard that talk about peak pressure, these evaluations. I'm assuming that everybody can still hear me loud and clear. As if somebody wants to just shoot me a quick little message. So here under ISO section 7.4.1, we have very similar wording. The standards are almost rubber stamps of each other. A lot of the wording is identical. The intended purpose is very, very similar. So our peak pressure study, which went on from I think 1990 something or other, 1998, for about 4 or 5 years. We thought we'd be done in the first year, but we didn't complete it until 4 years later. What we discovered there was that there are a variety of peak pressure formulas out there, most of them supplied by either the agent or the equipment manufacturers. And these are three. I'm not identifying which one they are. There's a couple problems with how they were created, three altogether actually. One is that they assume that the relationship between pressure and peak flow rate, which is what causes peak pressure, is a square root relationship. It's not a square root relationship. So these are mostly square root relationships. This is not a square root relationship. So this is the data that we took. The other thing is that they were not taken at the area of interest. The area of interest is actually in a leak to volume ratio of about here, somewhere in this range, and because the enclosures are tightened down, so we get a 10-minute retention time, so we kind of know how tight the enclosures are. So the data was actually probably taken somewhere in this area, I'm not sure, but it wasn't taken in the area of interest, and it wasn't taken over a wide enough sweep. So when we did the peak pressure research, what I did is I said, okay, what would be the range of enclosure leakages that would occur from different protected heights and so on, and let's measure the peak pressure in that area of interest. So that gave us a series of points that described a curve, something like this. So you'll notice that once we get down in around a very, very high peak pressure, that we're starting to agree. But in the area of interest, which is around 250 pascals, you can see that there's a huge difference between the peak pressure formulas that are out there and the actual peak pressures that we got when we did our research. In addition to that, if there's anything in the room that has a lot of heat, these peak pressure values will be even higher. So this is discharged into a cold room. So the message there is that the existing formulas, the existing data, I guess, is under-predicting peak pressure by 200%, sometimes 400%. So that's the first thing that people say when they run the new equations. Say, oh my God, VDS says that we're going to have only a quarter of the pressure that you say. Our data was done over a wide range, and more importantly, the data was taken in enclosures that were measured in the same way that we measure them with the door fan. So if we have an enclosure leakage area, there's a lot of different ways of measuring enclosure leakage area. And in order to make sense of this, we have to be measuring the enclosure leakage area in the same way that we're going to be measuring the enclosure leakage area on the job site. So there hasn't been the correct correlation when manufacturers over the past 10, 15 years, whatever, have been creating their peak pressure formulas because they're not measuring enclosure leakage the way we are going to be measuring it in the field, so we get the proper relationship. So for all those reasons, the existing peak pressure formulas out there don't predict anywhere near the peak pressures that we're actually getting. So that's the bad news. The good news is that these enclosures will actually take a lot more pressure than we thought they would. I think that peak pressures in the range of 1,000 pascals are commonplace and get experienced all the time. We just haven't come to accept that. And the way that we evaluate that is with what we call our fantastic integrity software. I think most of the integrity tests done worldwide have been using our software since 1986. Roughly around 3,000 different companies that have been using it on a regular basis. I would guess that probably 1 million tests have been done with our software in the past. The addition that we have now is the peak pressure part. We say venting and peak pressure analysis has been added. We did have a peak pressure analysis in our old CA2000, which was the best information that we had in the year 2000, which unfortunately was not very good, and a lot of it was manufacturer's information. We now have much better information, which is the reason why we are no longer supporting our old CA2000 software and going with our fantastic integrity, because it's the one that gives the right answers. So there's various questions here about the performance of different agents and so on, and it's simply a matter of putting those agents into our software and pop, it gives you the peak pressure values. So we'll be going over that in more detail as we progress. I don't have anyone helping me out this morning, so we're not going to be putting answers in too many questions as we go. If I notice one that's particularly germane to the topic, I'll space with it. So I want to see if I can move on to the next. This is a dual acting PRV. You can't actually tell it's dual acting just by looking at it. In fact, it might not even be a dual acting. But these dual acting vents can be ordered, but more importantly, they can be measured with your door fan. Whenever I get one, I slap it into a cardboard box and I apply some pressure with my door fan, and I want to see how that vent performs. They just about always perform very differently than the manufacturers say they perform. So, and then sometimes there's something about the vent itself or something about the installation that prevents that vent from performing properly. Very, very easy to use your door fan to check these vents. I like to have them fully open at around 80 pascals or so, 100 pascals in that range. This fan system we have here is probably very similar to the fans that most of you have. We've developed what we call a contra-rotating fan that will measure PRVs at 500 pascals and put out 4,000 CFM at 500 pascals and make flow measurements. Normal fans won't do that. If that's something that you're interested in to measure the performance of your PRVs, by all means, talk to us about it. So now we're on the hold time part. So we've covered the pressure relief venting. Now we're into hold time. The driving force for hold time is primarily gravity, at least in most cases. Agent leaks out the bottom, air comes in the top, and you get an interface between the two. There are dynamic discharge pressures that occur when the agent releases that we've talked about. These peak pressures, even though they may be quite high, there's an assumption that these peak pressures result in a lot of agent being lost. In fact, they don't. Particularly with halocarbons, because there's so much cooling. When the agent is released, the agent's not going out, but air is coming in. So we're actually increasing the mass inside the enclosure because we're cooling it. So we don't actually lose anywhere near the amount of agent that we thought we were losing. Particularly with halocarbons, we wind up keeping almost all the agent that's discharged. The formulas say that you're going to lose, if you do a 10% concentration, you're going to lose roughly 10% of your agent. In fact, you lose like maybe 1 or 2%. As a result, if you're discharging, let's say 10%, you actually wind up with a 10.8 somewhere in there most of the time. Not quite the same with inerts, because there's not as much cooling with inerts. There's a lot more mass of agent going into the room. The concentration formulas for inerts do allow for much more losses. So in both cases, you will get more concentration than the manufacturer's equations dictate. The next thing that will push the agent out are static pressures. In some cases, we might have pressurized control rooms, pressurized rooms on either side, up, down, or sideways. We have to go around the enclosure, measure the pressure underneath all of the doorways to find out what the pressures would be during the discharge. And very simply, that's how we do it. In some cases, stack effect will cause a static pressure. Buildings that are very, very high, sometimes we can have a 50 pascal stack pressure. The kinds of pressures that we're dealing with in these enclosures due to gravity are 1 or 2 pascals for inerts and 10 to maybe 15 pascals for halocarbons. So stack can be huge. Leaky dampers in the HVAC system can cause agent to get sucked out, and wind can also blow the agent out. For many years I put proposals in for wind losses, which I think can be the same as gravity losses. Can't seem to get anyone to pay attention to that. They are still real in enclosures that are exposed to wind, and wind can be the major driving force. That would probably fall under the section that requires special engineering or something, but something that needs to be considered. So NFPA employs what we call a sharp interface. So it says that at time equals 0, the agent fills up, or the enclosure fills up with agent. Agent runs out the bottom, and we've got a layer of air on top, as you can see here, as time progresses. The ISO assumes that we have an ever widening interface, a slow mixing between the agent and the air. In fact, the truth is somewhere in between those two, and these agents, when they come into the room, have what we call a characteristic thickness. Most of the time, that for halocarbons runs around about 0.2, 0.3, 0.4 meters to about 1.1 meter for an inert. So it's not an ever-increasing interface thickness. It does get thinner. In fact, we've noticed that as agent comes out, the interface, instead of widening, actually gets narrower. And we have all the documentation for that, which is the reason why we've come up with new equations that ISO has accepted for what we call not the wide interface, but the thick interface. And Todd Hetrick of 3M and myself worked on this. He did his master's thesis on that, and I consider he and I to be the two world experts on interfaces. Fortunately, all the information that we have on that is in the standards at this point, or in our software. Now, someone said the sound is completely gone. I show that my sound is working here. If anyone else can still hear me, it's back now. Okay. All right, good. Thank you very much. Hopefully I wasn't saying anything important during that time. So in this section here, we've got 9 options to pass both peak pressure and hold time. So essentially, the name of the course is Optimizing Enclosure Performance, and this is how we optimize it by looking at what these options are that allow us to pass both peak pressure and hold time. Now, I've improved this from the previous versions by showing you examples in each and every case. So there's all 9, and we'll run to the first example. So the first example is the more agent that we put into the enclosure, the longer the retention time will be, and it allows us to have a leakier enclosure, which means we're going to have less peak pressure. The reason why these enclosures create peak pressure is we tighten them up so they have the appropriate hold time, and then we go, whoops, we got too much peak pressure. So in this example, we've got a ceiling void where very commonly in the US we do not flood the ceiling void. In Europe and most other places they do. So using our new software, I've got 2 of them here. I've got the before and after, if you will. One's kind of superimposed upon the other. So we've got pretty much identical enclosure. This is 10,000 cubic feet, 10 foot high. This is what would happen if we flooded it and our minimum protected height was 9 feet. We would require a PRV of just over a square foot. If we flood the above ceiling space, we increase our volume, and we increase our maximum protected height. The minimum protected height stays the same. We're still protecting to the same height, and so on. But this allows us to have much more leakage in the enclosure, which means we don't have to install a vent. Like, it might sound like I'm encouraging people never to install vents, but I know a lot of cases people don't want to install vents anyway, but this is the way you can do it to get both hold time and peak pressure in the enclosure. The other way of looking at it is that I'm showing you a design technique that will improve both circumstances. Looking at it the other way, if we keep the total flooded height as low as possible. We're not improving fire protection, we're not improving the hold time, we're not improving the peak pressure situation. So that's the first example. Number 2 is to lower the protected height for the descending interface. Doesn't make any difference for continuum mixing, but for descending interface it does. So here's another example. So this is number 1, and then I've got number 2 kind of superimposed. The only thing that I've changed here, I've changed the minimum protected height from 9 feet down to 6.5 feet. You'll notice here again we need a vent. Here we don't need a vent. The reason why there's a difference is this enclosure does not have to be tightened as much as this enclosure does, so that we've saved money in not having to air seal it so much, and we've allowed it to pass both hold time and the peak pressure requirement. I can't tell you how many times I come into a room and they've got racks that go up to 6 inches from the ceiling, and they want that room to be tightened up enough to give them the required hold time, and it's virtually impossible to do that. So we have to know that we want as much agent on top of the protected equipment, not the smallest amount of agent. Seems kind of intuitive, and it is. So the next one is to specify continuous mixing. This is probably one of the most commonly misunderstood features of hold time, is the whole continuous mixing thing. It's assumed that there's equipment at a certain height, there's a minimum protected height, and there will be descending interface. I think there's only descending interface roughly about half the time. There are thermal effects inside the room, particularly with the inerts, that cause the agents to get mixed. There are often cooling fans in the equipment that are sufficient to have the agent mixed. So you might say, well, gee, how do I know? Well, I know from when we do a test on an enclosure, I go around with smoke and I look at the movement patterns, and if I see that air from the equipment cabinets going all the way up to the ceiling and going in big convection loops, I know that they have mixing in that room. So the good news there is, if you want to protect equipment at a very high height, mixing is the way to go. So let's go to the next slide and see an example. Again, 2 enclosures. I've done 2 evaluations here side by side. The only difference is this is a descending interface. This one is continuum mixing. You will notice here that I've increased the concentration from 7.5 to 10%. So let's say that the design concentration was 7. Over here we got a little bit of extra, 7.5. That's fine. Here the criteria is, how long does it take for the descending interface to fall to 9 feet? That's the performance criteria. Over here, the performance criteria has changed. It now becomes, how long does it take for the initial or the design concentration to fall to 85% of design? If design was, let's say, 7, then 85% of that, I believe, is 6.3. Don't quote me on the numbers, but the principle is the same. So here our performance criteria is the concentration that we want to fall to, and in continuum mixing, notice I've added more agent. In fact, about 1/3 more agent, and this is totally necessary when you're doing continuum mixing. It's not that the design has gone up, the design is still the same. If the design was 7 before, it's still 7 after. But the I think I call it extra design, or there's not really a good term. In NFPA there's like 6 or 7 terms that describe concentrations, but there's not a good term for it. But we don't want to hold 85% of 10%. We want to hold 85% of the design, which is 6.3. Again, that enables us to get the hold time that we want, and also we don't require a vent. I guess my idea here is that the enclosures are intrinsically safe. We don't want to put in design aspects into the enclosure that rely upon vents to be working. We want them, if the vents happen to fail, then we're still kind of okay. So we're talking about design characteristics in the room that will make the rooms intrinsically safe. And these are 2 examples of mixing. I don't actually see this very often, of mixing fans. I do see air conditioning units that are dedicated to the room that allow the agent to be circulated, usually sucked out of the subfloor and up through an air conditioning unit, blown into the room and going around and around in circles. This is probably the most common. I'm just going to take a quick look at your questions here to see if there's anything on there that's important. It sounds like you're all hanging in there pretty well. So Robert Lowry says, I always understood that adding more agent only caused the agent to flow out faster. That is true. Whenever we put in more agent and it flows out faster, what tends to happen with descending interface, the more agent that we put in there, the faster it flows out, so the faster the interface drops. Continuum mixing is a little bit different because if we increase the initial concentration to 10%, it will drop to 9.9, 9.8, 9.7, etc. everywhere in the enclosure. So it takes longer to drop from 10% to 6 than it would be to drop from 7.5% to 6, if that makes any sense to you, right? In fact, often 4 times longer to drop from 10% to 6.3 versus 7.5 to 6.3, only in continuum mixing. We have to be familiar with continuum mixing and throw it into our calculations as we just did here to see, oh, looks like continuum mixing may solve a problem that we have here. Often, if I hear about an enclosure where they want to protect right up to the ceiling, I say, you got to put in more agent and you have to make sure you have some kind of mixing in the enclosure and run the mixing, the continuum mixing calculations. Both standards, ISO and NFPA, have continuum mixing calculations, and recently, in the most recent version of NFPA, the continuum mixing calculations give a longer and more accurate retention time than we had before by around about 15–20%. So we actually have a little bit of an improvement there, requires a little bit less air sealing with the new version of the standard. Our intention being there is to give an accurate picture but not require a whole lot of air sealing when it's not necessary. Now the other question about hold time and height, when we're looking at continuum mixing, we assume that the concentration is the same everywhere in the enclosure. So everywhere in the enclosure, it starts at 10, drops to 9.9, whether at the ceiling or the floor. We may get air coming in at the ceiling level that gets continually mixed, churns around with all the other agent that's in there. So should be every point in that enclosure with continuum mixing would be the same concentration. So now the next one is to increase the enclosure pressure limit. I know for a fact when peak pressure first came out, people said, oh my God, let's say that we only can withstand 2 PSF. That's the way we'll be safe, right? Or for the, in pascals, around 100 pascals. The problem with that is that it's unrealistic and somewhat unachievable. It's even hard to get a vent that opens fully open, that's fully open at 100 pascals. So we know for a fact, as I said earlier, that these enclosures are regularly experiencing 500, 750 pascals and so on. The only study that I've been able to find is this one. I can't remember who did it, but it was it's in a publicly available paper. It's not our information, and it shows that a regular 2x4 stud wall, 16 inches on center, can take 13 pounds per square foot, which is in terms of pascals, that's it's about 50 pascals per PSF, so that's around about 650 pascals. As we go up to 2x6 walls, they get a little bit better. So these are the guidelines that I use normally for a well-constructed 2x4 wall, sheetrock on both sides, supported at the top and bottom. It will easily handle 250 pascals or 5 PSF. When you go to 2x6, it's up to 10 PSF. You go to 2x8, it's a 15 PSF. You got reinforced concrete, easily will take 20 PSF. This does not necessarily include concrete block walls. Concrete block walls can crack very easily, and they look solid, but they're not always solid. They need to have rebar reinforcement in them in order to withstand those kind of pressures. They need to be reinforced and have rebar running from top to bottom and also be pinned at the top. Sometimes these concrete block walls are just basically sitting there, and unfortunately we have pictures of them, of what they look like when they get knocked over. Not a very pleasant sight. So reinforcing these concrete block walls is important. The other thing that happens with concrete block walls, which is interesting, is because the block walls don't give it all when the discharge occurs, they tend to create more peak pressure, about 30% more peak pressure with a concrete block wall versus a gyprock or sheetrock wall. The sheetrock wall might move even 1/8 of an inch, will reduce the actual peak pressure by around 30–40%. Seems unbelievable, but you can do the calcs and prove it to yourself if you really want to. Our testing has proved that, so beware. So number 4 is to increase the peak pressure limit. So here we show a peak pressure limit of 250 pascals and we need a vent. We bump it up to 750, all of a sudden we don't need a vent. So that's all it takes. This calculation, which is running in Excel right now, we have released it to some of you, but there have been some calculation problems in it, and we are in the process of putting it on our website, and also so anybody can use it, and also putting it into our software. The calculations that this does is exactly the same as the enclosure integrity software, except it looks at it from the other point of view. Currently, the enclosure integrity software assumes that you're building an enclosure and then you test it for peak pressure and you test it for hold time. If we're designing an enclosure, we don't have anything to test. So we're looking at it from the other standpoint. What we're looking for is, what is the gap between the leakage that I need for peak pressure and the leakage that will create the hold time that I'm interested in. And a properly designed room will have a gap between those two. The more overlap they have, the more that we have to rely on vents. So this software is designed to show you various scenarios. Over here you can change the venting equation you're using, the standard that you're running, whether you got interface, initial concentration, all of the factors. You notice humidity is in here as well, the humidity range that you're looking at, and do a dry run before you even install the system. In a lot of cases, if I was able to take a look at the design before they built it, I could tell you, you're going to have problems with this. You need to change this and this. The cost of changing it at the design phase is very, very small. The cost of fixing it 2 days before the room is occupied is very high. So that's why we have this tool there, and that's why we're talking about it. So I'm just going to take a quick look at some of your questions. Some of them look pretty interesting. So I'm just going to scan through them. So a question someone asked is, the pressure limit required by FM200 is around 1,000 pascals, and the SFP says it reaches 600 pascals and negative. Why should I install a PRV? Now, the manufacturer, you may say that the peak pressure that's going to be created is around 1,000 pascals, but the question here is, will the walls take 1,000 pascals? That's the question. Will the enclosure take it? Who will stand up and say the enclosure would take 1,000 pascals? In fact, you'd be hard-pressed to get anyone to say it'll take 1,000 pascals. So what will typically happen is they'll come back to you and say, well, the enclosure pressure limit is what it's called in NFPA, is 250 pascals. Now, whoops, now all of a sudden we need a vent. Someone said, asked a question about enclosures with huge glass windows. There's no reason why windows can't take 500 pascals. It happens all the time when the wind blows. It depends on how they're constructed and whether the windows will pop out of the frame. I've actually had situations where the enclosure owners, or the owners, were so paranoid about this peak pressure that they weren't willing to say it would take any pressure at all. And I just turn on my door fan and say 500 pascals, the enclosure's at 500 pascals right now, and it's fine. 500 pascals is not a big deal. The other thing that happens with enclosures, since I've seen enough discharges to know, is when the enclosure starts to let go, it's not like popping a balloon. You hear it creaking and groaning and all kinds of horrible noises happen long before there's any kind of failure. Doing our peak pressure study, we regularly took our enclosure up to 1500 pascals, and at 1500 pascals you can see the walls, the 2x8 walls, visibly bowing an inch or so, and they're starting to make a lot of noise. So if you increase the pressure in the room slowly and it starts making a lot of noise, then you back it off. You'll find that you can probably take these rooms up to 250 pascals with your door fan, and actually prove it to yourself that way at the very least. You can take your office up to 250 pascals if you want to. The fans that we have, the high power fans, are very good at creating pressures around 250. If we want to measure them at that, we need what's called a contra fan. If you want to go up to 500 pascals, you also need that contra fan. So there are ways out. So someone asked, should we perform the door fan test before running the calculations? In terms of the order that things happen in, you have to perform the door fan test when the enclosure is completed. These calculations need to be run well in advance. So using this design tool that we have here, if you go through our training course, by the end of it, you should be able to run through all these calculations before the enclosure is built. Once the enclosure is built, you can't go around changing a whole lot. Okay, I'm just kind of going through your questions here, and yeah, I'm going to have to carry on here with the presentation because it's already hours up. So in this slide here, we show 3 different agents and their peak pressures. This is something that we can, again, determine ahead of time. We'll notice that with FM200 and Novak, at around 15 square inches of enclosure leakage, the peak pressure values are, positive peak pressure values, relatively small. I think we have this backwards here. Apologize for that. This inert, this should be a positive peak pressure over here. So these have the same retention time, and all of them have peak pressure values over 250 pascals. So, but you'll notice that the enclosure leakage that creates that hold time is much different. So the hold time is the thing that determines how tight the enclosure has to be. In this case, we can say that a typical time around 11-12 minutes dictates that the enclosure gets tightened down to this level. That's what creates the peak pressure. Next one is extended discharge, which you can also run a calculation on that. Very commonly used with CO2, not so commonly used as with the other agents, but it should be looked at as an option. This is something that we've been forced to install in some enclosures after the fact, just to maintain concentration when we found out they're incredibly leaky, very expensive to do that. We can get some kind of an idea ahead of time. We can, take a look at what the hole size would be if we've got a very leaky enclosure. We can make some design considerations, and as we saw in the previous slide, notice if we're looking at a leaky enclosure that the inert can be much, much leakier, so that tends to favor the leakier enclosures. Sometimes they have enclosable openings and so forth. Number 7 here is to reduce hold time, and both standards require a 10-minute, a default of a 10-minute retention time, or the amount of time it takes for response by trained personnel. ISO says unless otherwise specified by the authority, who probably not going to specify it most of the time, but it's something that needs to be considered in the design phase. If you have a very small enclosure and you've got trained personnel that are within minutes, you could actually have a 2 or 3 minute retention time. We bring this up because of these really tiny enclosures that they have, very, very difficult in some cases to get a 10-minute retention time. So we need to know that ahead of time. It's called the small room problem. It's our most pervasive problem, literally hundreds if not thousands of calls on the same problem. I've got a small room, I've air sealed the heck out of it, I got a 2-minute retention time, and I can't get it any tighter. Some of the other features that we've talked about earlier are important to consider. Having as high a possible maximum protected height, putting in as much agent as possible, possibly considering continual mixing, taking a look at the agent that we're using. All of these decisions can be made in the design phase so that we don't wind up with problems when we go to test. I think what I'll do is I'll keep carrying on with the presentation, and at the end I'll just continue to answer all the questions that you have. Again, this will be online so you can watch it. So number 8 is to close isolation dampers at the end of the discharge. So typically all the isolation dampers are timed so they close and then the discharge occurs. My suggestion here is a lot of situations you can actually close the dampers after the discharge. You're not going to lose much, if any, agent most of the time, but that's an evaluation that can be done. You essentially get what I call a free pressure relief vent by doing that, and particularly for existing installations where they've had excessive peak pressure, I said just change the timing sequencing with your dampers and you can get the free PRV through the HVAC system. So it's something to be considered. And the next one is to reduce the lower leaks. Many situations where the only way that they can pass is to measure the leakage distribution. Both standards allow you to do this. It's actually cheaper, easier, and faster to measure the leakage distribution than it is to try and fix it. I've known rooms where they've spent $50,000 trying to seal them up tight enough to pass when all they had to do is to measure the leakage distribution, which we can do in a number of ways. First of all, here we've got a leakage split of 0.5. You notice that we need a vent. Here we can have an enclosure that's much leakier, which means we spent much less money in trying to get it tight. We've got a leakage split of 0.1, which is allowed in NFPA. ISO allows 0.15, and we don't need a vent. So that's kind of an indication as to what happens when you measure what's called the leakage split. And here we've got 3 enclosures that had excessive peak pressure. We measured the leakage split, which meant we didn't tighten the room down so much, and they passed the retention time requirement and the peak pressure time requirement. And how we do that is we can cover the ceiling in plastic, which I've done, I think, 5 times in my life. Each time you do it, you swear you'll never do it again. There is a faster way to do it. Sometimes this might be the only way to do it. And the faster way to do it is to use 2 fans, where this fan is measuring the enclosure leakage. This fan is neutralizing the pressure across a suspended ceiling, which you need. And the new feature in our new gauges will allow the operator to control the pressure across here to 0. So we'll set this fan to the pressure we want in the enclosure. After we do that, we set this one to 0, and the 2 of them will wobble back and forth for a while, for a couple of minutes, until they stabilize. We used to have to do this with 2 people. We now can do it with 1. So we've improved that process, and our level 3 shows ceiling neutralization is, I think, one of the most powerful testing tools. I can typically do this in about 20 minutes more than doing a regular enclosure integrity test. And probably past 25% of my enclosures doing this test, maybe a little less. And here we are. This is a graphic that shows one fan that's neutralizing the pressure across the suspended ceiling. The other fan is measuring the room leakage. So it's a major part of our training course to show you how to do that. And there's another graphic there showing you the same thing. And yet another one. Another version of this is called the subfloor only test. So here we're measuring the pressure across the subfloor. We're pressurizing the room to neutralize the pressure across the subfloor. So we're measuring the subfloor only leaks. This is one way to measure leakage distribution as well. It's allowable in the NFPA, it's allowable in ISO, and this will tell you what the leakage is below the floor, and another way of measuring the below ceiling leakage area. So typically what happens with people when they get involved in this testing, they have a nasty little problem, they phone us and we can offer them a solution, a testing solution. The purpose of this course is to show them how to design an enclosure in the first place that doesn't need fancy testing solutions. But barring that, we're usually stuck with having to test what we've got, and there's a bunch of things that we can pull out of our tool bag to try and get these enclosures passed. So 5 design tips I'm going to share with you. One is the PRVs need to open early. The vents need to be high in the room. We do have to measure the vent area. And actually each one of these I think has a slide. So we'll just jump to the slide. Here we show a series of peak pressures with vents that opened at different points. This vent opened at 250, this vent opened at 50, and so on. We don't want to wait until the very last minute to open our PRV because the pressure will build up and spike right past the pressure limit for the enclosure. So these peak pressures happen in a couple of seconds. So if our vent opens at the peak pressure, it will go right past it. So that's why my guideline is that I'd like to see my vents open at least by 125 pascals. Next point is when we vent as high as possible, we're venting air, not agent typically. Usually the agent is heavier than air, and that allows us to keep more agent in the room, which is a good thing. If there happens to be a suspended ceiling across here, there'll be a velocity across that suspended ceiling. There's a way that we can measure that. We don't want to take the suspended ceiling with us. So in this case, if the vent's up here, we need vents in the suspended ceiling if there is one, so we don't blow the suspended ceiling out, which will only handle about 50 to 100 pascals maximum, unless they have that super heavy duty suspended ceiling. Next one is that the vent area needs to be measured, and it's simply a matter of, first of all, seeing how much the vent opens at, I like to test them at 125 pascals. I notice how much the vent opens and I hold it there, and then I measure the vent path with the door fan in both directions to find out how much venting path I have. The enclosure needs to be set up to venting conditions in order to do that, which may require different door openings and closings and such. But the essential piece here is that the door fan will tell you whether your vents work, and it will tell you how much venting you have. That's the number that goes into the equations to see what the peak pressure is. Just because you buy a vent that has a vent area of 1 square foot does not mean you're going to get 1 square foot out of that. You may only get half that or even a quarter of that. So by actually measuring the vent area, we put the proper number into the equations and determine what the actual vent area will be as opposed to what it was supposed to be in the design, which is the reason why we have failures. So pressure relief vents is vents open partially, they open too late. I like to actually measure the vent before I even install it. I just slap it in a big cardboard box and put my blower door on the other end and measure the pressure in the box, and I watch it to see how it opens before I even take the time of installing it. I know several of the installers I've talked to have had multiple vent failures, and in one case they relied on the pressure relief vent manufacturer's specifications as to where the vent opens, and they somehow got pascals and psi screwed up, so they had a failure there. And then the next time they installed the vent in the wrong direction, and I think they had a third failure. So after that they said, Colin, what we do now is we turn on the door fan. If we don't see that vent open, we panic. We make sure we see that vent open when the door fan turns on. This would be one example why, if we had this type of flap, for example, on a Halocarbon, it would close on negative pressure, and whoops, it's not going to work on the negative side. These can also be, it says do not obstruct. I'm sure everybody pays attention to that. Often they are obstructed, or they're rusted shut, or the dumpster's pushed up beside it, or whatever. Duct is crushed. I found ducts full of debris. Vent dampers stuck. It's surprising what you find. When you measure it, you find out that I would say that the almost half of the vents that I've measured have one kind of problem or another. Not serious enough to stop them from functioning altogether, but certainly a significant problem. Electronic dampers may not open. They need to be checked in the annual inspection to make sure that they will open. In some instances, if those dampers don't open and the system discharges, you may create more damage due to the discharge than the fire vent itself, which may not even be a fire, may be a false discharge. So, or they can be installed backwards, which I've seen. Or here we are, I call this the ceiling vent. Earlier I talked about recognizing that the suspended ceiling will only take about 50 pascals, 100 pascals maybe. This damage could be caused by velocity from the nozzles, which I don't think, or could be caused by excessive pressure in the room. And the enclosure is trying to vent through the suspended ceiling, but it's taking the suspended ceiling with it. And so in this case, we need enough vents in that ceiling, and there's a very simple way that you can measure that with your door fan to determine whether there's enough venting in the ceiling, which is oddly enough in our training course. And then the fifth one is to run the enclosure calculations in the design phase. Take a look at peak pressure, take a look at hold time. Look at the variables that you can change easy in the design phase and make those decisions. And when people have questions, they often phone us and we say, well, in this situation, if you do this, do that, you'll be fine. If you do that, you won't be fine. So we got a brand new enclosure integrity training. We no longer support our old software simply because it doesn't handle peak pressure properly. We don't want to have the liability of saying, oh, well, we used your software and it said it was okay. That's why we no longer support it as of the end of this year and are encouraging everybody to use our new software. Our training is online. It's miles ahead of what our training was before. We're encouraging everybody that uses our new software to go through the training and to get certification. Level 1 is for HJs and FPEs. Once they go through that, we're happy to answer their questions and so on because we know the body of knowledge that they have, and we don't have to explain the basics to them. So along with our training, we offer support. Currently, our training certification period is 3 years, and there's a recertification fee after 3 years. We are adding new material to our training course all the time, so in 3 years it'll be quite different from what it is now. The other support feature that we insist on is that people will be using our new software, not our old software. So having a combination of a new software and new training will give you all the support you need and answer any peak pressure or enclosure integrity or hold time question you may have. This is the final slide, oddly enough, I think. Yeah, this is the final slide. If I haven't answered your question, send me an email at Colin, C-O-L-I-N, at Retrotec.com. Now, I'm going to go to, I've got a juicy selection of questions here, and I'll just continue as long as you people stay on the line. We still have tons of people on there, and go through and answer as many questions as we can. So we've got a really good question here from Paul Jennings, who's probably one of the most experienced testers out there. He works out of the UK. If you ever need any support on the UK or testing done or whatever, he's the man. He may have done more enclosure integrity tests than anyone on the planet, I'm not sure, but certainly has bags of experience. So he says, let's see if I can actually, yeah. We recently found pneumatic PRVs on an Argonite system 8 years old, which no one knew if they would work, nor was there any means of testing it. The end user has now instructed their fire maintenance company to modify the Argonite system by fitting valves and a place to fit a small cylinder to prove the PRV open. So it's really important that when we look at these enclosures, we see those kind of warning signs that, like, okay, we've got a pneumatic PRV over there. How do we know it works? If it doesn't work and the building blows up, you know, I don't want to be responsible for it. So I need to tell you about that. So that's a good one. So Dave Palmer is asking a question about does trained personnel mean people trained as firefighters or company staff familiar with the room, with the enclosure? That's a really good question. I don't know that they may have a definition there for it. Often standards have things that are pretty loosey-goosey, and they say, oh, the authority having jurisdiction can decide. Well, in fact, most of the time the authority having jurisdiction can't decide. They probably don't have enough knowledge to figure that out. Should be the FPE that decides. Unfortunately, as the enclosure integrity tester, I'm often put in a position of having to make those decisions and say in my report what I think makes sense. Situations like that, if you're not sure, just send us an email, describe the situation, and often what happens is we will contact the HJ, have a conversation with them and the design team, the testing team, and so on, and come up with something that makes sense. So Dave goes on to say, to do lower leak tests with a fan above the ceiling, does the ceiling area above the ceiling have to be contained, i.e. walls extending to full height? It needs to be contained to some degree. We have to be able to establish pressure up there, otherwise we can't neutralize anything. In a number of instances, we have a suspended ceiling that covers many, many rooms, and we pressurize the entire cap. We open the doors to those rooms to relieve the pressure. We can still get there. Our new fan with a 24-inch diameter Flex Duct, our high power fan, will pump a lot of air into an above ceiling space and will handle around about 10 square feet of holes, which is a lot. But there are limits, and it does work a whole lot better if we have containment. Initially, when we started looking at enclosures, we had a lot of enclosures that where the wall stopped at the suspended ceiling. Not a good idea from a smoke containment standpoint or any other standpoint. We are seeing more and more in the US, we're seeing more and more walls going slab to slab. In Europe, they're doing a much better job of containing the enclosure, running the walls slab to slab, providing what we call passive protection, containment of the hazard. The reason why we need to do that is that we probably have more risk due to smoke versus fire. So if there's smoke goes up into the suspended ceiling area, it can discharge your system and cause all kinds of havoc. So we need to contain it, not just from a hold time perspective or for that reason, but we need to be containing these hazards to protect them from a variety of things. And smoke is probably more important than fire. I don't think we have too many of these rooms burning up, but we have lots of smoke events. Robert Locke was asking, is there a way to get a copy of the slide presentation? We will have the complete video of everything that you've seen so far on our website, probably in a week or two, or on YouTube. So the past ones are on there. This one is a little more comprehensive than the previous, so might be a better one to watch. But that would be your avenue for that information. So Paul Jennings again is saying, the question of enclosure strength in existing enclosures is often compromised because of poor records. No one is willing to sign off on a particular strength. This is 100%, no doubt, and nobody wants to stick their neck out to even say it'll take 100 pascals. So crank your door fan up to 100 pascals and say, well, I know it'll take 100 pascals. It's taking it now. If the enclosure won't take 100 pascals, it's probably walls are made of tissue paper. 100 pascals is not a lot of pressure. It's almost our test pressure. So yes, that can be a problem. And I'm not sure what the answer is. I'd be interested to know. Okay, another question here from Paul. So the height of the plasterboard wall increases, say from 3 to 4 meters. The effective strength decreases. True. The longer the wall is, significantly because the deflection. Also, the European plasterboard manufacturers seem to be saying that explosive strength, i.e. a discharge, could be significantly less than their quoted test strengths. I contacted the Kitta-Fenwal PhDs. I ran this by them and I said, is there a difference between a peak pressure of 1,000 pascals and a steady pressure of 1,000 pascals? And they said no. They are essentially the same thing. 1,000 pascal spike actually produces a little bit less deflection because there's momentum in the walls and you've got to pick them up and get them moving in a certain direction. But our conclusion was that there is no difference between static and dynamic pressures. Like they may be thinking of pressure spikes that aren't representative of the actual pressure that's like, for example, if you hit something rapidly, then it's hard to measure the pressure spike. But we are actually have measured these pressure spikes accurately, so we know what they are. So I wouldn't say that's a problem. So Sean Hendrick, who unfortunately is left, said we typically put the PRV wall strength question back on the engineers. There's no consistent wall strength. The resource is true. Also, the enclosure is only as strong as its weakest link. True. Lots of data centers have windows. True. If we look at architectural studies for windows and so on, we'll notice that even in a relatively modest wind, you can get 500 or 1,000 pascals on a window. And if they're an exterior grade window and they're properly mounted in their frames, then they should take a reasonable pressure. The problem with glass, I guess, is that depending on what kind of glass it is that it is breakable, and when it breaks, you get a big mess on your hands. So I would be, if I was interested in this, I would be inclined to get a small window, put it in a test box, and crank it up to 500, 1,000 pascals and see what it did. I'm just running over your questions here to see if any of them haven't been answered. John Ellen was asking, is annual fan testing a code requirement in NFPA 2001 or ISO? Both NFPA and ISO say the same thing. They say that there must be an annual inspection, and if any doubt exists, then the door fan test must be repeated. Well, it's hard to say that there's no doubt because you don't know what's happened since you were there a year ago. I suppose you could do a detailed inspection to find out that no changes have been made. If you see changes, then obviously the test has got to be repeated. But I know in some cases that they've actually doubled the size of the enclosure. When we were there last, they've put additions on there. No one said anything about it. The enclosure integrity test in some areas is seldom repeated. But it does say if any doubt exists, it must be repeated. So they're kind of saying in a way that needs to be repeated. And there's at least 10 countries that require annual retesting. At least the authorities enforce annual retesting. So depending on how you read both standards, you can say that annual retesting is required. There's an annual inspection that most of you do anyway on your fire systems, and it's worthwhile taking a look at the enclosure again, and rerunning the door fan test is not the end of the world. And it's starting to be more and more common to be done more and more frequently. So someone was asking what model of door fan can be used to test small to larger rooms, also test ceiling voids. Testing smaller is usually not a problem. If you're only testing tiny enclosures, we have tiny fans that will do that are easier to move around and so on. But if you're testing a range of enclosures, our high power fans will test big and small. They'll go right down to something the size of a broom closet, so usually testing small is not a problem. If you get one of our double fan high power systems, you can test pretty well 99.5% of all the enclosures out there, either with Flex Duct or large enclosures. What happens when these enclosures get tighter? They require less blowing power in order to test them, except if you're doing suspended ceiling systems, you're using a lot of blowing power to test the space above the suspended ceiling, which can be quite leaky. And in addition, the extra blowing power is needed to test the vents, whereas before we might have been able to get away with, say, 1,000 or 2,000 cubic feet per minute, maybe 5,000 cubic feet per minute. When we start testing vents at 100 pascals or so, all of a sudden we need a massive amounts of airflow in order to measure them or even to get them open. So we are getting people using more of a high power fans. They work particularly well on 240 volts. They kick out almost 2 horsepower, blow like almost 8,000 cubic feet per minute. They will operate at very high pressures if you want them to. I think it's the ideal fan for doing both PRV testing and enclosure testing, and kind of does it all. Now someone said, is the room integrity test compulsory? All the standards say that the hold time evaluation must be performed, and the door fan is the not the approved method, but the anyway, there's wording in there that says you can do it with a door fan or some other method. There has been no other method that anyone's done since 1984, so that's the only method that I'm ever aware of. So door fans are what is used. So essentially what it means is that door fan tests are mandatory for every clean agent enclosure. Used to be that it was mandatory for hold time, and it's now mandatory for peak pressure. So, and if that doesn't get you, then you really should be testing them just for your own safety, to know that that system you walk away from is not going to blow up when the system discharges. So someone was asking about our 3000, a two-fan 3000 model. The model this gentleman was talking about is two 3000 fans, and it will test anything and everything. It'll test BCLA tests for suspended ceiling. It'll test subfloor. It'll test vents. It's the big daddy. If you have that system, you probably will never need to buy another one from us. We've got people that have been using our fans for 15, 20 years. We've been making them for 32 years, and that one will be running a really good long time. So yes, that'll test anything and everything. I think that's answered most of the questions you've had out there. Can't see any questions I haven't answered. If I didn't get to your question, you can send me another question saying, hey, what about this question? We still have a number of people online hanging on, so I'll give you another couple of minutes to conjure up your question before we sign off. So we've been at it for about an hour and a half now. I think this presentation went reasonably well. So someone was asking the question, how do we get peak pressure from current data? I'm assuming you mean current door fan data. The old NFPA test did the test at 10 pascals. The new one does at 10 and 50. We can still use 10 pascal data or any data that we want if we do it at a series of pressures, 10 and 50, or as ISO does from 10 all the way through, a series of test points up to 50. It will give us a more accurate and longer retention time and probably reduce the requirement for the PRV as well, which is a reason why we have the new test method for NFPA that tests at 2 points instead of at 1, and the reason why we get better results. So we can use the old test data, which is usually referred to in leakage area, if that's all we have, but it might be a little bit conservative. Someone's asking me if there's another webinar this evening. We actually have one at 11 o'clock on large building testing, but not for fire, but for, well, energy purposes, I guess, a different purpose for the same equipment. So this one started at 7 o'clock our time. The next one starts at 11, so that's 4 hours from the starting time. If you go to our website, www.retrotec.com, you can sign up for that, and that's free. So let's see, another question. So someone was asking about calibration. The fans have got to be calibrated, I think, every 5 years. The gauges annually. Usually what we do with the gauges is we have a gauge exchange program. In a lot of areas now we have a network of distributors worldwide at this point, so there's usually somebody close to you that can do a gauge exchange for you where you send out another set of gauges and then you send yours back for credit. If you have enough time, you can send yours in to be calibrated and send them back. There's a fair amount of shipping involved, so usually what they will do is to have calibrated gauges in stock so they can send them out to you right away. So that's how we handle gauges. It's annually, and the fans are every 5 years. And we not only go through and do a calibration of your gauge, but we do a complete checkout, and you usually wind up doing a complete maintenance on the fan as well. In a lot of cases, for some of the older fans we had there, the 900 series fans and so on, the new fans have got a lot more power than the old ones, more efficient, stronger, longer, faster. So in a lot of cases where you can exchange fans as well and upgrade, trade them in and so on. So, someone says, Colin, I reckon I got your first equipment in 1988, so that would make it 25 years. So someone was asking in the Middle East, how long does it take to get one calibrated one back? We have an agent in the Middle East in UAE right on your doorstep, so they are getting very seriously involved in this and will be able to service you locally for your needs. And if you have some question about that, by all means get a hold of us, but I think they're doing a good job. They've put on a few training courses and are starting to provide some local service, so they should be able to take care of all your needs. The enclosure strength statement, I believe we sent out a copy of my paper. There's an ISO version, an NFPA version, and it quotes the source of that table. If you don't have that article, let us know and we can send you a copy of it. We might be doing a follow-up and might send you a copy anyway, but I think that we send it out ahead of time, but I'm not sure. If you don't have that, just send me an email and I can send it off to you. So again, Scott was asking about sending it to webinar participants. I'll take a look at that. I'll talk to our marketing department about sending that paper out. I thought we'd sent it, but Scott, it sounds like from what you say that we didn't send that off, so I'll send that article. It's the ISO version in particular. It's about 30 pages, pretty heavy going, but it does describe a lot of this in very technical detail. The presentation I did is kind of designed to put it in a context that will be a bit easier to understand, a little less technical, but what you really have to do. The paper is a little bit technical, but there are some references in there that will be useful. I think you can also download that from our website under enclosure integrity testing. If you poke around there, you should be able to find those papers as well. But by all means, I will see about sending that out to you. So someone asking for my email address. It's Colin, C-O-L-I-N, at retrotec.com. I thought I put it up on the slide, but it looks like I haven't. Retrotec with no H on the end. I'd be happy to answer your questions, or you can send it to support@retrotec.com. So Dana is asking about in an energy protected rooms, there are plywood walls constructed inside the rooms. Is advisable to have this type of walls? We don't consider ourselves to be fire protection engineers per se. We're the guys that are involved from the moment of discharge to the end of the discharge to the end of the hold time. Whether or not the system will put out a fire, we don't consider ourselves to be experts in that area. So in terms of combustibles and what's going to burn and not burn and so on, that's a fire protection engineer type of question. Now, if you're not already on our mailing list, for sure send us an email with all of your details and we'll put you on there. So Javier is asking, have you already been able to justify the use of experimental results, talking about LVR instead of the existing formula? I'm not sure what you mean by are we been able to justify them. I know that the experimental data that we took is correct. I was there, I took the numbers. All of the agent manufacturers and equipment manufacturers were participants in that study to one degree, that they're there for a day or 3 days or a week or so on. 3M was there for every one of them, I believe. FIKE was there for every one of them. So it wasn't just me doing it in my backyard. It was under intense industry supervision, and we had people coming over from Europe that witnessed certain stages of it and so on. We had the agent manufacturers, the equipment manufacturers installing their tanks, installing their valves and so on, and discharging them all into the same chamber. So I think the justification of using experimental results is that it's just more accurate. I mean, I think it's the right number, you know. Okay, I think we've pretty well run out of juice here. So you get any more questions, you have our email address. We'd be happy to talk with you.